Welcome to another deep dive. This time into a world where, well, survival of the fittest isn't just about, lions and gazelles.
It's about algorithms.
Algorithms.
Yeah.
Solving really complex problems. We're going deep into evolutionary algorithms.
Yeah.
And how the principles behind billions of years of evolution can actually power the algorithms that are shaping our world. It's pretty mind-blowing.
And what's so fascinating about it is that nature has kind of been running this huge optimization experiment for, millennia, right? Like evolution itself is about, how organisms adapt and thrive in all these crazy different environments.
Right.
And that actually provides like a blueprint for algorithms that learn and adapt just like living things.
So it's like the same processes that, shape the Galapagos finches could help design a bridge.
Exactly.
Or optimize a traffic system.
Yeah.
So we're essentially saying that these algorithms, they're not, unlike traditional programs, they're not explicitly programmed, are they? They evolve.
They evolve.
And they improve based on the data they're given.
Exactly. It's like instead of having those rigid instructions, it's more about a system that actually learns and adapts by itself.
Right.
It navigates this complex landscape, and it's trying to find those best solutions on its own. And that's where those genetic algorithms come into play.
Ah, yes. Genetic algorithms. I feel like that name itself, it kind of makes me think of digital DNA evolving inside a computer.
Yeah.
So can you break that down for us a little? How do these algorithms actually work?
So imagine this whole population of potential solutions to a problem.
Okay.
Each one is represented by this digital genome.
A digital genome.
Yeah, it's basically like a set of instructions that defines its characteristics. And then these solutions, they go through a process that really mirrors natural selection.
All right.
So the fittest solutions, the ones that perform the best, right, they get to reproduce.
So the algorithm is breeding better solutions, just like nature kind of selects for those advantageous traits, right?
Mm-hmm. Exactly. And their digital genes are actually combined to create offspring. So a whole new generation of potential solutions.
But is there a risk then of kind of getting stuck in a rut? Always just breeding from that same pool of successful solutions.
That is where the element of randomness comes in, right?
Yeah.
So you have these small random changes that are introduced, just like mutations in nature.
Okay.
And these mutations happen in the genomes of the offspring, which adds variety.
Okay.
And that allows for potentially superior solutions that you wouldn't have thought of.
So it's constantly experimenting, trying new things, just like evolution, kind of.
Exactly.
Throws up those random mutations.
Throws them up there.
To see what sticks.
What works.
But how do we know, how effective are these algorithms really? Can you give us some, real-world examples?
Oh, there are some really cool examples.
Okay.
So John Koza, he's a pioneer in the field. He actually used genetic algorithms to design electronic circuits. And some of these were so unique, they were granted patents.
Wait, algorithms are inventing patentable solutions?
Yes.
That's blurring the lines between human ingenuity and computational creativity.
Exactly.
Wow. So are we saying then that algorithms aren't just mimicking human intelligence, they could be surpassing it?
They could be surpassing it in certain areas, yeah. And this is even further, shown by the U.S. Patent Office, granting a patent to a whole factory optimization system.
Really?
That was designed completely by a genetic algorithm.
Wow. Okay, so it seems like evolution is a really powerful framework for designing learning algorithms.
It is.
But how does this approach compare to other machine learning methods? What are the strengths, the weaknesses?
Well, evolution, it's great at tackling complexity. It might be slow, but it can really shape those intricate structures just like you find in biological systems. And that would be almost impossible to design from scratch.
Right.
So think of it as creating the blueprint, the underlying architecture for learning.
So evolution provides the framework, the structure. But it's not necessarily the fastest way to learn, is it?
You're right. It's not. Evolution takes, millions of years. That's where other learning methods come in.
Right.
They're great at fine-tuning and optimizing within that framework.
So it's like a block of clay. Evolution gives you that initial shape.
Yeah.
But you need other tools to really mold it into that masterpiece.
That's a great analogy.
So the real magic happens when you kind of blend evolution with other methods.
Precisely. You can use the evolutionary algorithms for the structure, that framework of the solution, and then use other faster learning algorithms to really optimize within that framework.
So it's like teamwork.
Teamwork.
And this brings us to another really interesting aspect of genetic algorithms. Schemas.
Yes.
And I understand that these are kind of like building blocks of successful solutions.
Yeah.
So can you explain how they work
Yeah.
and why they make the search process more efficient?
Schemas are, well, think of them like patterns and combinations of genes that have been proven effective in the past.
Sure.
And they basically act as these guides. They kind of direct that search process towards more promising areas of the solution space.
So instead of just randomly combining solutions,
Right?
the algorithm actually prioritizes these proven building blocks.
Yeah,
So it's learning from its past successes.
exactly. It's like evolution itself, right?
Totally.
It's favoring those advantageous traits.
So by focusing on these schemas, these genetic algorithms can actually speed up that whole process of finding the best solutions.
Yeah, exactly.
Much faster.
Much
So
faster.
it's, I don't know, like searching for a needle in a haystack, but you have clues.
You have clues, yeah.
You have hints that kind of point you in the right direction.
Yeah,
Makes the search way more efficient.
way more efficient.
But with all this talk about, algorithms designing circuits, optimizing factories,
Right.
it makes you wonder about the very nature of learning, doesn't
It
it?
does.
Like, are these algorithms truly learning? Or are they just following, I don't know, pre-programmed instructions in a really clever way?
Well, it's a great question.
Okay.
It really digs into the very definition of learning, right?
Right.
Because while these algorithms are, based on instructions, their ability to adapt, to evolve, even to create these novel solutions, it suggests a form of learning that goes beyond just rule following.
So they're discovering patterns, making inferences,
Yeah.
and generating outcomes that weren't specifically programmed into them.
They are.
That's incredible. So we're seeing this blurring between what we think of as programmed behavior and true learning.
We are.
And that brings up some other really interesting questions, doesn't it?
It does.
Like, if algorithms can learn and invent, what does that mean for, I don't know, the future of work, creativity, even human intelligence?
Big questions.
Yeah, big question.
Those are questions that we're going to have to grapple with as a society.
As machine learning keeps advancing.
As it advances, because the potential is huge, right?
Yep.
To augment human capabilities, to solve problems, to drive innovation.
But it's important that we navigate all this very carefully, right?
Very careful.
Thinking about the ethical and societal implications along the way.
Absolutely.
You touched on something really important, that as these algorithms get more sophisticated, more capable of independent learning, decision-making,
Right.
that this whole idea of transparency and explainability becomes even more important.
It does.
Can you talk about that a little bit, like
Yeah.
this concept of opacity in machine learning? Why does it matter?
Yeah. So opacity, it basically refers to how difficult it is to understand how a machine learning algorithm actually reaches its conclusions.
Okay.
It's kind of like a black box, right?
Okay.
We put data in, we get results out,
Right.
but we don't really know the reasoning.
I don't know why.
We don't know why.
And that can be problematic.
It can be, especially when these algorithms are making decisions that affect people's lives.
Right. So even though we design these algorithms, even when they're inspired by, something we understand like evolution, there's still this mystery to how they actually work.
There is, and that mystery can have consequences.
Right, because if we don't understand how an algorithm is making decisions, it's hard to trust those decisions, especially when they have big implications.
Especially then.
Like, I don't know, imagine an algorithm deciding who's eligible for a loan
Exactly.
or helping with medical diagnoses.
Right.
If we don't know the reasoning behind it, how can we be sure it's fair or unbiased or even accurate?
Exactly. And that's why transparency and explainability are crucial.
Yeah, not just for trust, but to make sure that these systems are used responsibly and ethically.
Absolutely.
We need to find ways to peek inside that black box, understand the logic behind the decisions.
The why.
That's essential if we're going to harness the power of machine learning, but also mitigate the risks, make sure these technologies are actually serving humanity in a positive way.
In a good way.
This has been a really eye-opening look at evolutionary algorithms.
It has.
We've covered so much, from the basics of genetic algorithms to the philosophical implications of AI.
We have.
But before we wrap up, I want to come back to this idea of evolution as that blueprint for designing learning algorithms.
Sure.
It's fascinating, but are there limitations to this approach? Is evolution always the best model for machine learning?
Well, evolutionary algorithms, like any machine learning method, they have their strengths and weaknesses.
Okay.
One limitation is they can be computationally expensive.
Oh, okay.
Simulating evolution in a computer takes a lot of processing power and time, especially for complex problems with large search spaces.
So it's not always practical, especially if you need speed and efficiency.
Right, exactly.
So evolution is a powerful framework for learning, but it's not a one-size-fits-all solution.
It's not.
There are trade-offs to consider,
Always.
just like with any tool.
Exactly. And choosing the right approach really depends on the problem, the resources you have, and what you're hoping to achieve.
So sometimes the unique capabilities of evolutionary algorithms, their ability to, handle complexity, find new solutions, adapt to change,
Right.
makes them perfect for the job.
The ideal choice, yeah.
But sometimes simpler, faster methods might be better.
Might be.
There's no silver bullet in machine learning.
Nope.
The key is understanding the different approaches,
Yeah.
choosing the best tool for the job.
For that specific job.
Feels like we're at this turning point,
It does.
in AI.
Yeah.
Creating algorithms that learn and adapt.
An invent.
Inspired by evolution.
Yeah. It's pretty amazing.
It's exhilarating, but also kind of, I don't know, a little daunting.
It is. It's both of those things.
We keep hearing about, AI surpassing human intelligence.
Right.
This future where machines are outthinking us, outperforming us.
Yeah.
Do evolutionary algorithms play a role in that?
Potentially.
Yeah. Could these algorithms that are based on this slow, incremental process of evolution, could they lead to true AI?
Artificial general intelligence.
Yeah, like the AI that rivals or even surpasses our own abilities.
That's the big question, isn't it?
It is. And it's a question it's been around for decades.
Scientists, philosophers, science fiction writers.
Everybody's thinking about it.
Yeah.
And while, the timeline and the implications of that are still uncertain,
Sure.
evolutionary algorithms, they offer this glimpse into what's possible.
We do.
Their ability to, create new solutions, adapt to change, learn from experience.
Right.
It suggests a path, doesn't it?
It does.
Towards more sophisticated AI.
Towards something more.
It's almost like we're handing over the reins of evolution.
To the algorithms.
To the algorithms.
It's exciting. It's scary.
It is both of those things.
Yeah.
But as we go into this unknown territory, we got to be careful, right?
Absolutely. We have
The benefits are huge.
huge.
But the risks
are huge too.
We have to be responsible.
Yeah. Responsible development, ethical consideration.
Front and center.
They have to be.
We got to make sure these algorithms are aligned with human values.
That they're used for good.
That they're developed and deployed in a way that's transparent and accountable and fair.
All of those things.
Because the future of AI, it's not set in stone, is it?
No, it's not.
It's a future that we're shaping.
With every algorithm we design.
With every choice we make.
Every decision.
And it requires our attention.
Careful stewardship.
Well said. Well said. This deep dive into evolutionary algorithms has been, well, I don't know about you, but my mind is blown.
Mine too.
We've looked at the connections between nature and computation.
The intricacies of genetic algorithms, schemas.
And those big philosophical questions about AI and humanity.
It's been a journey.
It has. And it's clear that we're seeing a real change.
A shift.
In how we approach computation inspired by, nature.
By the natural world.
And the most exciting part.
We're just getting started.
We're just at the beginning.
Yeah.
As we keep exploring this connection between evolution and computation.
Who knows what we'll find?
We're going to uncover even more, I think.
More insights, more potential.
The algorithms of the future, they might be shaped by
human ingenuity.
But also by evolution itself.
By the principles that have shaped life for, billions of years.
That's amazing. Thank you for joining us on this deep dive into evolutionary algorithms. We hope you've enjoyed it. If you found it insightful, share it with your friends, your colleagues. And don't forget to like and subscribe for more deep dives into all sorts of fascinating topics. Until next time, keep exploring.